Good morning, students. In this class, we will study Jacobians. So, what is a Jacobian? Okay, if u1, u2, and so on up to un are n functions of n variables x1, x2, xn, then the determinant del x of u1, del x1 of u1, del x2 of u1, and so on up to del xn of u1. Then second row del x of x1 of u2, del x2 of u2, and so on del xn of u2. Then continuing in the same way, last row del x1 of un, del x2 of un, and so on del xn of un. So this determinant is known as the Jacobian of u1, u2 and un with respect to x1, x2 and xn. Okay, it is denoted by capital J bracket u1, u2, un bracket close, or del x1, x2, xn of u1, u2, un, or j u1, u2, un upon x1, x2, xn. So this way, this kind of determinant is known as Jacobian. So what we do in it, we find out the first order partial derivatives of each function with respect to the variables of which the this is a function is. Okay, for example, u1 is a function of x1, x2, xn. Then what we do in the first row, differentiate partially u1 with respect to x1, x2 and xn, and put those partial derivatives in the row. Similarly, second row elements and all other row elements. Now what are the properties of Jacobians? If J1 is the Jacobian of u and v with respect to x and y, and J2 is the Jacobian of x and y with respect to u and v, then J1 into J2 is equal to 1. Okay, this is the property. So we will prove it. Now J1 is equal to, we can write it, u and v are functions of x and y. So we can write it like this: del x of u, del y of u, and then the second row del x of v and del y of v by the definition of Jacobian. Similarly, the Jacobian J2 can be written. Okay, x and y are functions of u and v, right? So the Jacobian of x and y with respect to u and v. So this is del u of x, del v of x. Similarly, the second row. So these are the two Jacobian. Now we have to multiply this. Okay, if we multiply, okay, we are writing these, okay, symbolically. Ux means del x of u. Uy means del y of u, partial derivatives. Similarly, in the second determinant, we can interpret the elements like del u of x and del v of x. Right. So all these are partial derivatives. So if we multiply them, what do we get? We get these elements: ux, xu plus uy, yu. Then second elements ux, xv plus uy, yv. Similarly, we can multiply these. Okay, so this is my first element of second row and second element of the second row. Again, differentiating u and v with respect to uv, we get. Okay, so yes, if I differentiate u partially with respect to u, then I get 1. And if I differentiate u with respect to v, I get 0. If v with respect to v, I get 1 and 0, like this. And we can expand, okay, we can have their expansion like this, that del x of u into del x of u into del u of x plus del y of u into del u of y. Similarly, all other elements, okay, these can be written. So now we can see these things. This is the first element of the determinant, previous determinant, first element of first row and second element of first row, and similarly first element of second row and second element of this is sorry, this is the second element of second row and first element of second row. So these are written like this: 1 0 0 1, and the value is of this determinant is 1. So this is how we prove it. Now coming to second property, if u and v are functions of r and s, and r and s are again functions of x and y, then Jacobian of uv with respect to xy is equal to Jacobian of uv with respect to r and s multiplied by Jacobian of r and s with respect to x and y. So in order to prove this, we take the right hand side, we expand this Jacobian and as well as this Jacobian. Their expansion gives me this one. What does this mean? Del r of u, del s of u, del r of v, del s of v, del x of r, del y of r, del x of s, and del y of s, by definition of Jacobian. Now we are again multiplying them as we did previously in property 1. So this is the multiplication. Okay, since u and v are composite functions of x and y, therefore this ux del x of u can be written like this. Okay, by the definitions of total derivatives, these expansion can be written like this. What does this mean? I am explaining the one. Del x of u is equal to del r of u into del x of r plus del s of u into del x of s. So similarly all others. So we can see these elements are somewhere here, ur rx plus us sx. So means this element can be written simply as ux, and then this will be uy, and then vx and vy. So ux, uy, vx, vy, and this determinant. And if we see, this is the expansion of del xy of uv, means the Jacobian of u and v with respect to xy. Okay, this is simply a notation. It's not something that it is a partial derivative of u and v with respect to x and y. It's simply a notation for Jacobian. Okay. So now coming to property number 3. If functions u, v and w, okay, these are functions, okay, are not independent, then their Jacobian will be equal to 0. Right? So now that is the Jacobian of u, v and w with respect to x, y, z is equal to 0 if u, v and w are functions of x, y, z. That is, if u is a function of x, z, v is a function of x, y, z, and w is also a function of x, y, z, then their Jacobian with respect to this x, y, z will be equal to 0. If these are not independent, then it will not be equal to 0. So this is application of Jacobian, that we can test the functional dependence and independence of functions by using the concept of Jacobian. Okay. Second thing is, in the double integration, wherever there is a change of variables, we can apply the concept of Jacobians over there. Okay, so we can see if there is a conversion of Cartesian to polar coordinates like this, if x is equal to r cos theta, y is equal to r sin theta, then the Jacobian of x, y with respect to r theta would be equal to r, and similarly the Jacobian of r theta with respect to x and y will be 1 upon r. So these concepts are also used over there also. So now this is a question: if r is equal x is equal to r cos theta, y is equal to r sin theta, then show that this is equal to this and this is equal to 1 upon r. So taking up the first part, del del r theta of x y, that is Jacobian of this with respect to r theta. So x r r x theta, y r y theta. This you know from the definition. So simply partial derivative of x with respect to r, that is cos theta, and with respect to theta it is minus r sin theta, and similar with the second one y, with respect to r it is sin theta, and with respect to theta it is equal to r cos theta. So just finding the value of this determinant, I get r. Okay, now taking up the second one, r theta, the Jacobian of r theta with respect to x and y. So this is rx ry theta x theta y. Now what is r? R is equal to square root of x square plus y square, because we know that r square. Okay, if we square x and y and then add x square plus y square, then that would be r square cos square theta plus r square sin square theta. So taking r square outside, inside what is left, cos square theta plus sin square theta, that is 1. So this x square plus y square is simply equal to r square, and therefore r is equal to square root of this. And then theta can also be obtained like this is tan inverse y upon x. Okay, from those two relations. So therefore, what is this? Del del x of r. This I have done it here. Del del x of r is equal to this square root of this. Then differentiating this partially, this function. Okay, I get 2 with 2 cancels, and I get x upon this, and this is equal to r, so x upon r. Similarly, we can find out y upon r, and the same way we can proceed with del del x of theta. So tan inverse y upon x, so this 1 upon 1 plus y upon x square into del x of y upon x. This we know. Okay, what is the differentiation of tan inverse x or tan inverse y upon x? So using that, now the partial derivative of y upon x is minus y upon x square. So just simplifying, I get y upon this, so this is minus y upon r square. Similarly, we can find del y of theta is equal to x upon r square. So what we did, we put those values here. Okay, we found these values and we put in the determinant. So now if I simply find the value of this, I get this x square upon r cube plus y square upon r cube, and it is equal to r square upon r cube, because r x square plus y square is equal to r square. So this is simply 1 upon r. Okay, this is rough work that I just told you. So thank you, students. In the next class we will continue with some questions on Jacobian. Okay.